Hi everyone, welcome to my video on differential equations. Today we're not just looking at it as an example out of your exam or textbook. We are going to look at some real maths, a real life example of how differential equations can be used to make projections, and predictions. Specifically, I've just brewed up a bit of coffee. I'm going to make a cup of coffee, and I'm also going to put some hot water into the glass. It's not boiling because it's been cooling as I've set up the experiment. And we are going to look at how the temperature changes as time passes. Obviously the temperature will be getting lower because it's colder in the room than the temperature of the water. But we want to know exactly by how much and see if we can predict, using differential equations, what the temperature of the coffee will be, what the temperature of the water will be after 15 minutes. So let's start off making a cup of coffee. So we're going to pour it in here. There it is. Water has already been boiled for that. Cold milk, so this is going to make the temperature a little bit colder. There it is. Perfect coffee made. Now when I drink coffee I like to let it cool for a little while. So after 15 minutes I reckon that's going to be perfect for me to drink, but obviously when I'm sat at home drinking coffee I don't know the exact temperature, I just know that's how I like it. Another prop that I'm going to use is my telephone, which I'm going to use for the time. So we're going to start a stopwatch. On 0 at the minute. So as soon as we take the temperature of this coffee with our temperature device, that is going to be our T equals 0. And I will write down the temperature of the liquid. Room temperature, measured by the thermometer, is 24 degrees C. So let's just write that up before we start, because we are going to need this. So, I'm going to start the timer at the same time I take this temperature. So we know that when T is 0, when we start our experiment, no time's passed yet in our experiment. Time is all relative depending on where you start. You can always choose where you want your T equals 0 to be. So at the exact minute, the temperature, let's go now. We'll have to let it settle a little bit. In fact, let me bring this up close so you can see it settling. Nice cup of coffee. So 49.6, bring it back, 50.4, 51.2, 51.3, 51.3, I've pressed the start button. 51.3 degrees. Right, so that we can compare the rate at which the coffee cools and the hot water cools, let's pour in our hot water. There we go. The only reason I'm not starting them both at T0 is because I can only obviously measure. It was hard enough starting the timer and measuring the coffee at the same time. It would have been impossible for me to measure two, remember the measurements, while starting the timer at T0. So I gave myself a little bit of leeway. 47 seconds. I'm going to record the temperature here, exactly at a minute, so hopefully it'll have time to cool, to settle. You know what, we're going to have to fudge our experiment a little bit. This is sometimes what happens with an experiment. It's not ever perfect. So when it boiled it will have been about 100 degrees C, but from 100 degrees C it's going to sharply drop. And at the minute it's saying about 72.9, but it's still moving around. So actually we're going to change T to 2 minutes in a sec. You can see that moving around. We'll sort it out one way or another, do not worry about that. One minute 50, 51, 54, okay, 72.8. So our hot water was 72.8 degrees at 2 minutes. Okay, we've just fudged it a little bit. Now we've got until 5 minutes, but as we just saw, we'll probably have to put the thing in. I'll put it in now, ready. I'm gonna have to drink this coffee with this dirty thermometer in. That's the way it is sometimes. Okay, be alright. So I'll leave it in there, and at 5 minutes we're going to write down our measurement. So we've got a little bit of time to talk about how to set up our differential equation. Okay? Now, what happens when things cool is, obviously if you've got a cup of coffee, it's going to cool a lot faster in the Antarctic than in the Sahara Desert, for example. Okay? So it depends on the difference between the actual temperature of the liquid and the outside temperature, the room temperature. So it's going to be to do with the temperature of the liquid compared to room temperature, which we've said is just 24. Okay? So the difference between the two, theta take away 24. Now, what we're talking about is the rate of change of that liquid, okay? The temperature of the liquid. So we're talking about the rate of change of a liquid with respect to time. Now it's proportional to, okay, theta minus 24. That means that depending on the difference between the liquid and the room temperature, it's called the law of cooling, that will affect how it cools down. So back to some GCSE maths, if d theta by dt is proportional to that, that means that there's some constant, okay, let's do it in a different colour, constant k. Now k will be negative because it's decreasing. If you wanted to put a negative there, you could. I'm not that fussy because I know when I find my k is going to go to negative. Okay? So what we're going to do is we're going to try and solve this differential equation. Now the technique that it uses is separation of variables. Okay? So what we can do is we can divide by this theta minus 24. So we get 1 over theta minus 24 d theta by dt equals k. Hope you can see how I've got that, just divided the equation. Okay? The time is saying 4:57, 58, 59, and it's 48.2. 48.2. See if we can do our maths in between what's going on here. We've got until 6 minutes. That is when I planned to find the next theta, the next temperature value for the hot water. Okay? So, looking at this differential equation, it's a separation of variables technique. What we actually do to this differential equation is we integrate both sides with respect to t. Okay? So we integrate this with respect to t. You can see I'm used to my interactive whiteboard with the different colours, but there you go. We integrate this side with respect to t. Now, looking back at the phone, it's on 5 minutes 55. Let's now get it in here. You see, I forgot to do that again, didn't I? We're going to have to change our measurements a little bit now. Okay. We'll go to 7 minutes. We'll sort it out, don't you worry. Doesn't always go perfectly. So you can see the temperature has, well, it's a bit all over the show because I've just moved it, but it has decreased from the 72.8. It burnt my hand there. Okay, so it's on 6 minutes 30. Well, what happens with this differential equation is we can cancel the dt's. That is the result of the chain rule. Okay? It's not to do with dividing and timesing. It's a result of the chain rule. But that means that the separation of variables lets us integrate this side with respect to theta, integrate this side with respect to t. Back to the timer. 7 minutes, 61.7. 61.7. Better do it in blue. So we're all nice. Okay, so we've got all the measurements we need. Now our plan is to know the temperature after 15 minutes without having to actually measure it. Okay, maybe we'll do 15 minutes for the coffee. Bit of improvisation here, and let's do 16 minutes for hot water. At home you might want to make predictions about what you think it will be. Okay, so time's on 8 minutes, we've got 7 minutes to try and solve this and make our prediction. Right, so this is separation of variables method for core 4 or any other calculus that you're doing, any other maths. It's a very important skill. When we integrate 1 over x, we get ln x. Okay? Now the chain rule, we're undoing the chain rule. You can call it integration by recognition, whatever you want to call it. Either way, we're going to get ln the modulus of theta minus 24. Okay? We don't need a plus c here because we're integrating both sides. So you can imagine you'd get a plus c and a plus d. You can take away this plus c from here, put it all together, it's a new constant. Call it e, okay? But because we just imagined that in our head, we can think, well, we'll call it 1 plus c, just put it on the right hand side. That's the first bit integrated. The second bit integrated is going to be kt. Okay? And we need now our plus c. Now if we take e to the power of each side, so e to the power of this, e to the power of all this, what we get is e and ln are opposites, inverses. They cancel, you get theta minus 24 equals e to the power of kt plus c. Now, remember back to indice rules. When you're adding in the power, that's the same as multiplying. So e to kt times e to the c. Now, e to the power of a constant just means that you've got your number e and you times it by itself however many times. Okay? It's just a constant. For example, if you put e to the power 7 on your calculator, you get a number. This is just a constant, so we can call this constant, say, a big A, capital A. Okay? We're going to call that A. So we now plus the 24 to both sides, and we get theta equals A e to the kt plus 24. Okay? Hope you followed this. You can always ask on the comment section if you don't understand what's going on, and I'll try and make it clear for you. So, that's our general differential equation. We've got boundary conditions here that we recorded. Now just up for the grand finale, I'm going to put that in the coffee ready. Okay? We're going to have to go to this side of the board now, and we are going to think, well, when t equals 0, then theta is 51.3. Okay? We put that into this blue equation. 51.3 equals A e to the 0 times k plus 24. Okay? So, e to the power of 0 is just 1. So we get 51.3 equals A plus 24. So A equals, I wanted to use my calculator here as well. Could do that in my head, but there we go. Yeah, let's try it. 51.3 take away 24. Okay, 27.3. So we've got a value of A. Now we need our value of K. Okay, so we get that theta equals 27.3 e to the kt plus 24. Okay, now we know t equals 5, theta equals that. So we're going to put in t as 5 and theta as that. 48.2 equals 27.3 e to 5t plus 24. We solve this, take away 24, divide by that, so we get e to 5t. I was a bit ambitious doing hot water and coffee. E to 5t, that take away that. 0.2, take away 24, divided by 27.3. Now we want to ln both sides. Okay, so ln of that, ln of all that. And that gets us just 5t, and then we just divide by 5. Okay, so k equals 5t 1/5 ln 48.2 plus take away 24. Sorry you can't see this. 27.3. The reason I'm rushing is we're on 14 minutes, really tight for time. So on our calculator, 0.5 times by ln of 48.2 take away 24 over 27.3, and we get minus, told you it'd be a minus, 0.06, etc. That's to 3 decimal places. Okay, so we want to know when t is 15, and we've got the e theta equals A, which is 27.3, e to the power of k, which is 0.06 t. Okay, it's come up to 15 minutes. It's come up to 15 minutes. The temperature is 45.2. As you can see, that's a real temperature, 45.2. Okay. Let's see what our estimated temperature is going to be. Okay. All we need to put in is t as 15 for the moment of truth. If you're at home, you might be able to do this on your calculator already. Hopefully you can see this. For theta, 27.3 times by e to the power of 0.06 times 15, okay, plus 24. Not going to press it yet. What we're expecting, what we're hoping for, is 45.2 or somewhere around 45.2. Fingers crossed. No. What's gone wrong? What has gone wrong? I owe you lot a big apology because I've just taken a pause from a video by a stroke of fortune that the recorder stopped filming, but then I looked back over my work and I thought, what has gone wrong? Because maths is good. It should not be that far out. Okay? So what I did, I looked over and I thought, here, where it says 1 over 5, I stupidly put in my calculator 0.5 in a rush. Obviously 1 over 5 is 0.2. Okay? So that means that the value that was up on the screen before, 0.06 etc., was wrong. The actual value of k is minus 0.0241 to 4 decimal places, or 3 significant figures. If we put these values into our formula, for t is 15 minutes, theta is still not perfect, but I think you'll agree it's quite good, just from maths, okay? Just from predictions of knowing what it was at 0 minutes, what it was at 5 minutes, setting up a differential equation. If you put this into your calculator, you get 43.02 to 2 decimal places. The real, we said, was 45.2 degrees. So that causes a lot of discussion that you should be thinking about. Why is it not perfect? Well, it would be perfect if our measurements were perfect. This is a bit of a flimsy thermometer. It rounds to 1 decimal point. That's not perfect, first of all. Okay? So we were already working with rounded data. Now, obviously it's just an experiment. We're just trying to get as good a guess as we can. Now, I promised you that we would predict the temperature of the coffee and the temperature of the hot water. We've predicted the temperature of the coffee. Pretty cold now. What I'm going to do, I'm going to rub all this off a board, and we're going to come back and we're going to solve, might have a quick coffee break actually, then we're going to solve what the temperature of the water is when I get back, and this will just carry on for you because I'm going to pause, and we are going to do all this working out but for the hot water. Okay? Right guys, I've had a nice long coffee break. The time on the phone is now 37 minutes, okay? Now don't worry, the temperature is currently 40.5 degrees C, okay? But because we're not worried about that going too cold, our differential equation should still work, and we can predict it after any amount of minutes we want. So as opposed to just me guessing 15 minutes and rushing, 16 minutes, as you can see, was very, very optimistic. I do that sometimes, but there you go. We're going to do the working out, see what time we're on, choose what time we want to predict for, make our predictions, and see what the real was and what our prediction gives. Okay? Now I'm hoping that we're going to get a little bit closer, but secretly I'm thinking we're probably not, because the time that we're leaving is longer. I've been thinking about this room temperature of 24 degrees C. The room temperature could be fluctuating slightly, and it might have been a bad reading. Okay? So that's going to skew our data a bit. Anyway, with all that said, let's get on with the job at hand. What we want to do, we've got all the same working out as before, because we've got the law of cooling, and we know that it's going to be to do with theta, the difference between our temperature of the liquid and the room temperature. And we've done all our working out with separation of variables to get this equation. Okay? Now what we want to do is we want to use these initial conditions. Now I've had a bit of a brainwave. Remember I said that it doesn't matter what you call t as 0, okay? It's still going to work. Now as long as we change our t here, you know when the timer says, say 39 minutes, as long as we change that to compensate, we can change this t as 2 to t as 0, because it makes the numbers a lot nicer. So let's say that after 2 minutes we're going to call that t0. Okay? Well, that means that after 6 minutes it's going to be 4. So if we want, we can call it t dash. Okay? So it's like a substitution really. T dash is the actual time on our thing, take away 2 minutes. Okay? Just to make it rigorous in what we're doing, the two t's are now different. Okay? But if I use just a normal t, you know what I mean. So, carrying on. Okay, this should really be a t dash, but we won't worry about that. We've got this, and we've got the initial conditions. So when t is 0, theta is 72.8 degrees C. So you can see it's quite a bit hotter than the coffee. Okay? And I actually burnt my fingers holding it before. So, what we're going to do is we're going to say, well, 72.8 degrees C is equal to A times e to kt. Now when t is 0, this whole thing is going to go to 1. Okay, so that's just A plus 24. So 72.8 take away 24. 24 is going to be 48.8. So we found our value of A easy enough. We want our value of K. Okay, so we've got theta 48.8 e to kt plus 24. We know the other initial condition, our other boundary condition, when t is 4, theta is 61.7. 61.7 degrees is equal to 48.8 e to the kt, where t is 4, 4k plus 24. Okay, so what we're going to do is we're going to solve this, take away 24, divide by 48.8, take 1 and divide by 4. I'm sorry if that's a bit quick. At home you can work that out yourself as well. It's just rearranging this equation. So k equals 1 over 4 ln 61.7 take away 24 over 48.8. If you want to be exact form, keep it as that in your calculator. Okay, I'm just going to round just for convenience of substituting in numbers. So on your calculator, 0.25 if you want it as a decimal, 0.25 times by ln of 61.7 take away 24 over 48.8, and we get minus 0.645. And that's to 3 significant figures or 3 decimal places. Remember, it's a minus because we're decreasing. If you'd have put a minus here at the start, which you're entitled to, that would just be a positive. When you put it in, it'd be a negative. Same difference, okay? So we've got a value of A, we've got a value of K. So we've got theta equals A, which is 48.8, e to the minus 0.645 t plus 24. Now, if we look on our clock, we're on 45 minutes now. Sorry it's taken so long. Let's predict it for t equals 46. Okay. Right, really sorry again. That's another mistake that I've just noticed. This is the first time I've done a video like this. The pressure is on. It's quite a long video I'm doing, but no excuses. Sorry for the mistake. Let's get on with it, okay? Basically, the mistake I made was it should have been 0.0 instead of just 0 point. So I've changed it here, and also, if we know our actual time on the clock watch, we need to add 2 minutes on to get our new time. So this is 48 minutes we're talking about. So right, really sorry about that. I've noticed another mistake that I've made. Basically, I'm not very good at putting things in the calculator and reading it out today, obviously. When I put this into the calculator and wrote it down, I missed out a 0. It should be 0.0, not just 0.645. Okay, same here, 0.0645. So I've changed the equations. Okay, now the other mistake is that when we're changing from our actual time on a stopwatch to the real time that we're doing in our equation, because it's take away 2 from real time, to go back we have to add 2 on. So that meant that when we were predicting for 46, we should have gone to 48. Obviously, because I messed it all up, we can't predict for 46 anymore. All we can predict for is the next thing coming up, which is going to be 55 minutes now, because I've made so many mistakes. So sorry. Okay, so we're going to try and predict for 55 minutes, aka add 2 on, 57 minutes. I'm not confident at all about how well this is going to work out because of a number of factors. Okay, but let's go for it all the same. We're going to be putting into our equation 57. On your calculators, because you'll probably do a better job than me at the minute, we're going to put in 48.8 times e to the 0 minus 0.0645 times by 57, add 24. And let's cross our fingers, hope this works. Right, we've got a measurement of 25.24 degrees. Okay, so that is our prediction. Okay, so after 55 minutes, okay, or 57, as we've changed it, we're predicting it's going to be 25.24 degrees C. I'm sorry to say, guys, but this one is pretty messed up. Okay, I can feel it's hot at room temperature. Let's just, out of interest, put it in now. Saying 55 on the clock. Taking the reading. See, it's 35.7 degrees C. Okay, 35.7. That is a bad estimate, very bad. Okay, so if you get something in an experiment that goes awfully wrong, well, what could have caused it? Let's just see if we can figure out what room temperature really is right now. Maybe because I've been working so hard in here, it's heated up room temperature. Okay, see, it's, as I'm holding it here, I don't know if you can see it close to the camera, but it's more like 25.6, 25.8. It's pretty hot. It's decreasing a bit there. But yeah, basically we failed on the hot water. For the coffee we did okay. But this video wasn't to try and get a perfect prediction, it was trying to show you how differential equations, what you're learning at A level even, with the separation of variables, is actually a very useful technique for solving these real world problems. Okay? It's settled now 24.7 degrees. Now that could make a big difference. Okay? So you win some, you lose some. Coffee, not bad. If we'd have used a better room temperature at 24.7, if you're at home thinking, oh, I wish that had worked a bit better, I'm not going to do it all on the board, but maybe try that to 24.7 degrees C, see if you get a better estimate. I'd be really interested if you let me know in the comments if that works or not. Okay? Thanks for watching. Sorry about the mistakes, sorry it's not quite worked out perfectly. If you do have a bad approximation like that, the more time that goes on, the worse your predictions are going to get, which is an interesting thing. Whereas it wasn't so bad there, it's got much worse here for the real thing, okay? Thanks for watching, hope you've enjoyed it anyway and maybe learned something. Any questions, just ask some comment, okay? Thank you.